Unmasking matrix magic, the secret formulas to transform any matrix. Discover the hidden power of matrix manipulation as we reveal the elegant equations that can reshape any matrix into symmetric, antisymmetric, real, imaginary, Hermitian, or skew-Hermitian form. So in problem 10, we want to, by explicit construction of the matrices in question, show that any matrix T can be written A as the sum of symmetric matrix S and an antisymmetric matrix A, B as the sum of a real matrix R and an imaginary matrix M, and C as the sum of Hermitian matrix H and a skew-Hermitian matrix K. Now, matrices are the chameleons of mathematics, possesses an uncanny ability to transform into various forms, each with its own unique properties and applications. Let's explore how any matrix T can shapeshift into these fascinating forms. Starting with part A. For a symmetric and antisymmetric matrices, we need the transpose property, okay? And so for a matrix to be symmetric or antisymmetric, blue or green respectively, we see that if I take the transpose and I get the matrix back, we're symmetric. If I take the transpose and get a negative of the copy of the matrix, then it's antisymmetric. Which we've seen things like this before. We know that cross products are antisymmetric, for example. So if S equals T, some symmetric matrix, then S also equals T transpose. And if we add these two statements together, we get S plus S, which equals T plus T transpose, gives us 2S equals T plus T transpose. Therefore, solving for S, we get 1/2 T plus T transpose. Pretty easy, pretty straightforward. Also, if A equals T, some antisymmetric matrix, then A equals negative T transpose. All we did was push this negative to the other side. Adding these together yields A plus A. We see the negative T transpose there, gives us 2A, and this equals T minus T transpose. So we see that the antisymmetric form has a minus sign in between. Now this plus minus structure is going to maintain itself throughout all of these questions. So what this says is that symmetric and antisymmetric are kind of alter egos. And so with the wave of a mathematical wand, we can split T into a symmetric S and antisymmetric A into their components. Here the transpose is the revealing part of the matrix hidden symmetries. And we'll see why that matters in due time, or if you remember from certain applications in the quantum mechanics book, we saw symmetric matrices had nice properties. Now, moving on to part B, for real and imaginary matrices, we need the conjugate property. For a matrix to be real or imaginary, the statement of the conjugate to be real must equal the thing itself. Similarly, if we have the conjugate for imaginary, we know we change the sign on everything. So this is the two things that we're going to make the form from. And so if R equals T, then R also equals T conjugate. So adding these together like we saw last time, run it through the same gauntlet, you see you get R equals 1/2 T plus T conjugate. Similarly, if M equals T and then M equals negative T conjugate, adding these together yields the minus with the conjugate. Same idea for both of them, plus minus structure holds. And so what we can say is that the real and imaginary are kind of like doppelgangers. So in the complex plane, T can manifest itself as real and imaginary twins, both taking on their forms. And the conjugate represents the way that the matrix unveils its dual nature in the realm of complex numbers. Pretty cool, nice little intricate dance there. Finally, the one that we like the most in quantum mechanics, put these two things together, and we get the Hermitian versus skew-Hermitian matrices. So to be Hermitian or skew-Hermitian, we have that if we take the conjugate transpose or the adjoint, we get the matrix back. We love Hermitian matrices. We saw this all the time in the quantum mechanics book, and they come up everywhere else in math too. That being said, to be skew-Hermitian, as you probably figured this out, we just need to have a negative sign on it. Run it through the same gauntlets that we had before, h equals t, h equals t dagger. Add them together, you're good to go. You see the plus sign there. I think you can already see the writing on the wall. If k is anti-Hermitian, or skew-Hermitian rather, then we get the negative with the dagger on the same side. Add them together, you see you get k equals 1/2 t minus t dagger. Again, plus minus structure, pretty self-consistent. Note that this makes sense for this one specifically because this is a conjugate transpose, so they both work together. That being said, Hermitian and skew-Hermitian reflections. So this is kind of like taking the quantum leap. T can split into a Hermitian and skew-Hermitian reflections, where the dagger denotes the adjoint of T, revealing the matrix quantum personality. And it dances quite a bit. This, although it's an AI picture, has quite a bit of kind of understanding this type of matrix unlocks a lot of the universe. So I really like this image. For some reason, it just captivated me. But that being said, these transforms showcase the versatility of matrices, allowing them to adapt to various mathematical landscapes. By understanding these forms, we gain powerful tools to solve complex problems, like generators to make images like this. That being said, physics, engineering, and machine learning are using these all the time. So best to be aware of all the matrix forms because guess what? They're used everywhere. So that was a fun video, and if this got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the fascinating world of physics. There's so much more to uncover, and I'd love to have you along for the journey. Special shout out to all the patrons, especially those giving feedback on these new round of videos. Very much appreciate it. If you want to join and be a part of the community, feel free. The link is in the description. Um, Coming into the new year, we're going to have a lot to discuss on what book to do next and things like that. So I'll be talking to y'all primarily, especially the handful that stay in regular contact. Thank you, thank you, thank you. Look forward to hearing everything you have to say, especially your courses coming up for this next semester. As always, thank you for watching, and until next time, stay curious.